This video describes the history of MODFLOW, starting with electric analog models based on interviews with the participants. Prior to the development of numerical models, electric analog models were used to simulate groundwater flow.
In the 1930s, it was fairly apparent to people who knew about flow that there was an electrical analogy to the groundwater flow equations or the flow equations for fluids, including oil and gas. So at the Carter Oil Laboratory, there was developed what was called the Carter Analyzer, in which they developed a network of resistors that were precision resistors that were set up to simulate the reservoir properties of a flow problem, and they solved those flow problems in the 1930s, and that was called the Carter Analyzer. They used precision resistors to do it. Sometime around 1950, the people at the USGS, particularly Bob Bennett, realized that you could solve the problem of flow using a resistor capacitor network that represented the aquifer and the storage coefficient. In other words, the resistor network represented the flow domain, and the capacitor network represented the domain of the capacitance or the storage in the system. And what they further did is Hsieh realized that if you used low precision resistors in the network, that the low precision resistors could cancel out one another. They would average out to some average value, and so you wouldn't have to worry about having high precision resistors everywhere. You could build a network of low precision resistors and still get a good answer to the flow equations for a regional flow problem. Okay, so they started then building resistor capacitor networks on a pegboard so that you could put the resistors on the pegboard and build this network out that described the aquifer system, and at each node, or you could add a capacitor that would represent the storage of the system. So by doing that, you could describe an aquifer system with this system of resistors and capacitors. Then you could exercise that network in which the electrical voltage represented the potential, the fluid potential, or hydraulic head potential everywhere in the system. And if you had the right function generators, you could simulate wells and injection wells and withdrawal wells and various boundary conditions and so forth for the system. So it was in effect a general solution to the flow equation, and you could build these up in layers that represented a multi-aquifer system. So you surveyed, based on the fact that they had this capacity to build these models, developed a laboratory in Phoenix where they were routinely building these models to simulate aquifer systems across the United States. So if you had a problem, you could go to Phoenix and simulate that aquifer, much like you would do with a numerical model today. There were certain advantages in going to Phoenix because, well, first of all, the guy who really was the father of this technology was Hsieh, and Herb was in Phoenix, and he spent his whole career with the survey in Phoenix. He wasn't about to move out of Phoenix, but he could move him. So the laboratory was built in Phoenix, and Gene Patton and the other guy, his name Gene Patton, and he had a cohort. I can't think of the guy's name right at the moment. But anyway, if you went to Phoenix, then Gene was running the laboratory, and he would sit there and assist you in setting up the model. And the beauty of that system was that Gene was a very good hydrologist, and so there was this quality control over building the models, because Gene would sit and help you formulate the problem, and since he was such a good hydrologist, you would get quality control from Gene and this other guy that I can't think of his name right at the moment. Okay, so anyway, this was a going operation in 1960 or so. These things were routinely built in Phoenix. Now the difficulty was, I mean, you had to have various oscilloscopes and function generators and so forth to exercise the network electrically. So there was a capital investment in having the function generator, the various readout devices and devices in order to properly stress the network. So people were unhappy about the fact that the things were built in Phoenix, and then even though, let's say you built one for Long Island, Long Island would like to have the thing on Long Island, they'd like to operate the thing in Long Island. Well, the difficulty was you had to have all this other peripheral equipment, and so people got unhappy about the fact that this thing was, even though they got solutions and they had interesting results and so forth, that it was pretty much based in Phoenix. So meanwhile, back at the ranch, the petroleum industry was developing technology to solve the basic flow equation on a digital computer. And some of the best applied mathematicians worked on the problem. They worked on the problem. This was a rather well-known problem in the 1960s, how to solve the flow problems for reservoir engineering. And they developed various different algorithms to solve the flow problem efficiently and reasonably efficiently, okay? And as I said, the mathematics was developed in the petroleum industry. So in 1967, 68, I taught at the University of Illinois, and George Pinder was there, and I said to George, I think we could take the petroleum algorithms and apply them to a groundwater system and solve the basic flow equations to replace basically what we were doing with the analog model.
A guy from the district would go out there and sit with Gene and his co-workers and talk to them about it, and they'd get together and they'd they'd quickly build a network. There was a resistance capacitance network, and they'd make their model. They gradually shut that down as digital modeling came in. And, in some ways, it's a shame because it was a wonderful way to learn. It was a wonderful way to learn simulation. It was so intuitive.
Okay.
And see things going, to see your equipotentials and all that kind of stuff. It was good fun.
The USGS had an analog computer lab in Phoenix where they built groundwater models using networks of resistors and capacitors. And as a student, I worked in that lab until it closed somewhere around 1973. Actually, it moved to Reston, Virginia in that year, so I couldn't work there anymore. And then I got on with what was called USGS Phoenix Subdistrict Office, part of the Water Resources Division, where they did water resources studies in that part of the state. I actually had 3 separate positions before I got my bachelor's degree in 1974, 3 separate USGS offices.
Okay. So you were working on some of the electrical analog models.
Yes, that's right. The big one that we were doing at that time was Houston, Texas analog model was a huge multi-layer electrical analog model. I believe the project chief, the groundwater scientist, was Don Jorgensen, Texas. He was having that model built there in the Phoenix lab.
So could you tell me how big was the model, both physically and in terms of number of nodes, at least approximately?
I don't remember the number of nodes, but it had, well, the resistors were put on these sheets of pegboard with, I think the poles had 1-inch spacing. And this one had, say, at least 2 or 3 of those sheets, 4 by 8 in each layer, and then it had several layers. It could be that one layer represented the Chico aquifer and one the Evangeline. So at that time, I didn't know much about groundwater modeling, and I was there to solder resistors, and on occasion I would help with model runs by putting a probe on nodes and reading voltages, which would then be converted to water level or head. So that was my really first introduction to groundwater.
Now you were at the Long Island office, and I think you were working with electrical analog models to begin with. Is that correct?
That's correct. That was the job, was specifically to work in the modeling project. Rufus Getson was the chief of that project at the time, and there were 3 or 4 people in the project because analog modeling is kind of labor intensive, and they were interested in me because of my general physics background. I had a lot of experience in the laboratory, research laboratory. Again, I went that way at my undergraduate work because I was interested in applied work. So I loved working with the equipment in the laboratories and all. So they had a lot of electronic equipment in the analog model lab on Long Island, because that's what it takes to run the analog model. You have to apply electrical stresses to simulate groundwater stresses, and then you have to read voltages and all with voltmeters and oscilloscopes and all. So I think I was a good fit for that job.
I think at that time they had already started using digital models. Is that your same memory?
That's my recollection, is the 2D digital models had started by that point, but they were very limited in size. Of course, it wasn't that the theory of 3D was unknown, it's just that the computers were limited. So we were using mainframe computers at that point for scientific sorts of applications. And the USGS was using an IBM mainframe it may have been initially in the Interior building downtown, but the USGS moved at some point out to Reston. So 72 is when I was in Long Island, and I think that was about the time of the move to the national headquarters building in Reston. But whatever, there was a mainframe computer, an IBM, that was either downtown initially, and then it got moved to Reston. And so our scientists used the mainframe computer wherever it was housed, and would use it by a remote batch terminal if they weren't located where that computer was. So, but anyway, so there was a little bit of digital modeling going on, but it was just in its infancy. George Pinder was one of the initiators. Peter Trescott, John Bredehoeft, Leonard Konikow was involved at some point. I don't know the exact years. Because I wasn't involved in that early on, other than I started taking USGS training classes and learned about that sort of thing. But for those first several years in the USGS, I'd say at least 3, I was just involved with finishing the construction of the 5-layer analog model of Long Island, which was kind of a rare thing to have a 3-dimensional analog model. And so I was helping to finish the building of it. It had already been maybe 80% built, but it wasn't calibrated. Mm-hmm. And they were trying to figure out how to operate it and all. So I was very involved in operating that model, where you have to add the stresses to it, put in resistor networks to simulate the recharge and wells and that sort of thing, and set up all these voltage generators, waveform generators to vary these stresses with time. And then at first we were reading it with an oscilloscope, and you would stare at the oscilloscope and there would be a curve on the oscilloscope, an electrical curve, and we would be trying to read 3 or 4 times off of that. So we would look at that, and there was a scale in the oscilloscope, and you'd read the time at the beginning of the stress and say, 10 milliseconds down and 20 milliseconds down. And usually that was 2 people at a time. One would look at the oscilloscope and call out the numbers. And then the other person would write it down, and they would be moving the probe on the just a little electrical clip to move from node to node on this model and write down those numbers. So it would take like a couple of hours to read all the voltages for just one simulation. But then you still had the numbers, and you had to contour them by hand or whatever. Well, when I came along, there was interest in speeding that up as we got into the operational mode, and so we bought a recording analog to digital oscilloscope, and bought an interface that would hook it up to a little mini computer, one of the earliest mini computers used in the USGS. This was a Data General Nova, similar to the DEC, whatever they were, PDPs. PDP-11 was in the same era, but the Nova was cheaper, so we bought this Nova. So now, instead of having 2 people do this, and then have a lot of work afterwards, we would put the clip on, one person pushed the button, it would record that location and send it to the computer. And then you move the clip, push the button. So you still had to go through each node, but it was much quicker and more reliable because you didn't have to read it, an analog screen. And so instead of taking, probably took all afternoon to do one by hand. And so now we could do it in like 20 minutes or something. Plus we started drawing contour maps of the results, or just printing out all the values on a map from that analog to digital recorder. So I was involved in all that. I did programming for that sort of stuff and all. Without actually I wasn't doing a digital model at all, but it was a lot of digital work at that point.
Groundwater modeling in the USGS built on work in the petroleum industry. George Pinder, Peter Trescott, and Steve Larson worked on some of the earliest models.
The codes I was developing and working on then really had a long history before I even got involved. The core of the code really was developed by John Bredehoeft and George Pinder, and goes back even earlier to work with Hilton Cooper, and a number of articles published in Water Resources Research publishing the results of their analyses. So when I started in the summer of '71, I had a code that John gave me, and he said adapt it to this problem in Colorado.
Bob Farbold and my original advisor left to teach in Canada, and John Bredehoeft came to replace him for a year. I don't know if he intended on staying more than a year, but he was there for a year. And John had understood the importance of modeling in groundwater flow, and he had experience with electric analog models and perhaps others that I'm not aware of, and he also had obtained some analytical solutions to some well problems. Some of those solutions carry his name. He had the idea that perhaps it would be possible to do what electric analog models did using the computer. John didn't have the background to do that kind of analysis himself. Just about that time, the machine at the University of Illinois became sufficiently powerful that you could do those kinds of simulations. So it was decided, and I can't remember the details of our conversations, that I would see if I could figure out how to solve the groundwater flow equations using the digital computer. At that time, there were no numerical methods courses that I knew of. They may have existed, but I simply didn't know about them. So I went into the literature to find out how this kind of thing had been done by others, and I studied the petroleum literature where at that time they'd made the greatest advances in subsurface simulation using models. So I basically taught myself what I needed to know about numerical methods, taught myself what I needed to know about the computer and how to code in Fortran, and I put the two together and began to investigate how to solve the groundwater flow problem, and more specifically, how to solve the aerial problem. In other words, the problem that involves pumping and an aquifer of a given thickness that has an aerial distribution. So I studied that for some time, and I can remember this well. About January, John says to me, well, I want you to finish by June. And I thought, really? I mean, I've only been here for 2 years. You expect me to do this all by June? I didn't say that, I suspect, but that's what I was thinking. So I put myself to the task of writing a model and applying it to an area that I had investigated when I was under the tutelage of Bob Farvolan up in Nova Scotia. So he had sent me up there to spend summers doing field work, so I was familiar with this particular area that I eventually modeled. I had done field work there, drilling and so on and so forth. I guess the next thing that happened was that John recognized the power of this methodology and decided that we would try and introduce this into the survey as a tool that might in some sense replace the electric analog model, which by its nature took a long time to create and a long time to actually use. So we had a series of short courses that we put together to teach this numerical modeling technology. And just for fun, I dug out a report that I did when I worked at the survey, or shortly after I worked at the survey, but it carries the survey's representation, called an iterative digital model for aquifer evaluation. And that essentially was the code that John and I would introduce in these short courses at the survey.
George and I and Peter Trescott was in the office. Peter got interested, and so he wrote the model that most everybody used. So there was the Trescott model, which Peter also did a fairly good write-up. You know, we had a good documentation for the Trescott model. It was basically the model that George and I developed, and then Peter took it and documented it, and that was the model we taught. So it was the Trescott model.
Mark McBride and I started building models. You know, one of the first ones that I constructed, I coded up the ADI thing myself so that I'd have one, but then, or I guess I used stuff that Pinder and Bredehoeft had done at the time. And so he and I we built a couple of different models. We had one of these sand plains. We had another with models of groundwater flow near some lakes, trying to figure out effects of sewage effluents on the lakes. So anyway, I got plugged into this modeling stuff. So then in 1975, I got transferred to Reston into the Northeast Region Research Branch. And I basically working with Peter Trescott. Pinder, I think, had already just left at that time to go to Princeton or wherever he went at the time. So even though George wasn't there, Peter was kind of taking over, Peter Trescott was taking over, you know, George's role. And so I started working with Peter. And I was working with Peter, and Peter was working on, George and Peter had pretty much finished the 2D USGS model at that time. And I looked at their code, I made a few changes to the code, and they very graciously had me be a co-author on their report. But that was the USGS 2D model at the time. But Peter had been working on a 3D or a quasi 3D model. So I got involved with Peter, mainly with the programming aspects of it, trying to make it run faster and operate better. I mean, Peter had worked out most of the theory, did a lot of theory and the basic coding. And the focal point during a lot of that work was on solution algorithms. That is, you know, how do you efficiently solve these equations? And one of the big deals then was the strongly implicit procedure. Was that, you know, because these ADI things or line successive over relaxation, you know, they just take a long time. They'll get there probably. But so the strongly implicit procedure was, this was great. It's getting more to a direct solution algorithm. And then I got excited about some other methods that have been used in the petroleum literature. One of them was called the D4 algorithm, where by ordering the equations that you solve on a grid, you create a matrix that's already half decomposed just by the ordering. And so you could increase the efficiency of it. It sometimes had a little bit of round-off problems at times, but all those direct solution algorithms did. But anyway, so I had coded up this D4 thing to add on to the 2D model. And then Peter and I were working together, mainly, it was Peter's work, and I was just kind of tagging along as a good programmer for him. But that became, obviously, those models, the 2D and that quasi 3D and the 3D, were the MODFLOWs of that era, back in 75 until 19, whatever, when MODFLOW actually came out. But anyway, what was transpired period was that Peter, well, first of all, Peter developed a brain tumor, and his health was deteriorating. So at one point he had to kind of phase out. But we had been doing these training courses for USGS hydrologists in Denver all the time, basically teaching them how to run the models, the 2D and the 3D models. And so, I came to know a lot of people in district offices and whatnot. So then I got called on a lot to help them with their application. But what would often happen is, oh, yeah, okay, your problem needs a little bit of something different. So we'd have to code up, or maybe I would code up something to add on to the model. So that it became these little add-ons kind of all over the place. And the higher-ups, in this case, John Bredehoeft, was concerned. Well, there was also this documentation issue that, you've got to document these changes that you make to the basic model. Because the basic model is described in the USGS report, but you've changed it, and you got to document. So this documentation became an issue that, every project had to, reinvent the wheel, documenting something.
Digital modeling was really coming on big then, and Bredehoeft had done a lot of this work. The models were getting better and better. Computers were getting better. I was offered a job as groundwater specialist in what used to be the Northeast region, which is the northeast quarter of the country. It was a job where I bopped around from different districts and worked with people on whatever they were doing. And I tried to push the idea of simulation as an investigative tool. When you got working on a problem, trying to understand the hydrogeology, and you started playing with models and just seeing what made the most sense. I thought that was the big, rather than prediction, I never did trust in prediction. But anyway, just playing with simulation to get to know how the system worked and putting that into words, I thought that was the big thing about modeling.
The USGS had these training classes. They did finite difference and finite element in the same class. But everybody came home and did finite difference. Because the finite element partly was less advanced, not mathematically. It's just like the problem with 2D versus 3D finite difference in computers. The finite element took a lot more computer resource to solve the simultaneous equations. Because to deal with the problem of computer resources on finite difference, the hydrology community developed all these special solvers that took advantage of the matrix structure of a finite difference grid, regular matrix, line successive over relaxation, and alternating direction line successive, and SIP, strongly implicit procedure, which made it much quicker, less computer resources to solve these simultaneous equations than you could do with the finite element. So finite element just took a lot more resources once you formulated the problem to solve. So finite difference continually stayed ahead in its capability of the kinds of problems it could solve. But the advocates of finite element were very strong and really said, we got to keep working on this because someday we'll be able to do this sort of thing. And it has the advantage that you can focus the grid on refinements on areas where you need more refinement and all. So, but that debate went on for years up until MODFLOW, and then when MODFLOW came along, then that seemed to moved ahead so rapidly that finite element people, although they kept working on codes, Cliff Voss and Torak worked some, Goode continued. The capabilities including preprocessor issues, were so great that there weren't that many users compared to finite difference. Answers are just as good either way, so it just was more a kind of practical aspect of using these models and the computer resources that made users choose finite difference.
In those days, you didn't really separate out a generic code from the field application. You started with a code, and then you went into the code and wrote Fortran statements into the code that would be specific to your field area. That was the general approach in the early, at least through the mid-70s, that most model users also had to know Fortran because they had to go into the code and be able to change the code and recompile the code to adapt it to their area. And this was cumbersome, inefficient, and provided a real incentive to develop the modular codes.
In the districts, they were starting to use models. So it was getting out of hand. And we had a lot of guys who were capable hydrologists but poor programmers, which is what I was, basically. Mm-hmm. And they were into making their own models. And I helped several of them with that. But as I said, it was inefficient programming, and a lot of duplication of effort by people in different districts. And everybody wanted their own model. Everybody wanted to make their own. No, none of those guys ever documented anything. So it was awful hard to pick up somebody else's model, use it, and know what you were doing. In fact, it was impossible. So that was one of the problems at that time.
On January 19th, 1979, a meeting was convened in Denver by John Bredehoeft, at which it was decided that a modular model would be created.
In 1978 or so, there was a meeting, a big meeting, in which people addressed this problem. And the consensus, and there were a lot of people, Jake Rubin was there, John Bredehoeft, and a lot of big names in modeling the field. And the consensus was that the survey should have a model that most of the people use, and it should have certain characteristics. Now, Jake Rubin was the big opponent. He was saying, this is wrong, guys should make their own models so they know what the model is doing, and they understand the numerical things. And when garbage comes out of the model, they know right away that it is garbage, and they know they've done something wrong, and they won't know that if we have one big, it'll get to be a black box, it'll get to be people. So Jake was the opposition. Mm-hmm. There should not be a USGS model, I remember him saying. You had a good point, because the black box mindset became a problem. But but the other problem was bad. I didn't say much except that whatever we did had to be thoroughly documented, and they got tired of it.
John Bredehoeft thought that, well, look, what we need to do is we need to make this program modular, so that what we could do then is, okay, somebody could build a module, all they have to do is document the module, and anybody else can pick it up. They don't have to redocument it, they just point to this thing and away you go. And then there was a guy in New Mexico, Doug Posson, I think his name was. And Doug was a big type programmer, but he was I don't know what else he did in terms of the modeling, but he helped people in I think it was in Albuquerque or wherever, do the modeling and whatnot. But anyway, he was big on, I can't remember what the term was, top-down programming or something anyway. So,
structured programming?
Structured programming.
Okay.
So anyway, he kept emphasizing structured programming. John's out there with, we need a modular program. So I got assigned that project in like 1978 or thereabouts, maybe 1979. Okay, Steve, you're going to build modular code. So I started, and I had a 2D modular code, and I also had started on developing 3D versions of the modular code. And it was all nice little concise module. I still use it, the one that I made, for lots of things today.
I had long since become a advocate, a believer in modular programming. In other words, not trying to do everything all at once, one gigantic design, get all the pieces designed perfectly and then sit down and write the code afterwards, but rather to develop portions of the code and modules of the code to do certain functions or whatever, and then test those individually because they're easier to build and easier to test, and then assemble that into the greater model, whatever that might be.
To the best of my knowledge, the start came in late 78 and early 79 through basically the ideas of someone named Doug Posson and John Bredehoeft. John at the time was the head of the National Research Program in the survey, and Doug was a hydrologist and computer specialist. And this is where I don't know the backgrounds of what the relative contributions of those two were, but somehow they came to the belief and were in a position to push for the development of a generic modular groundwater flow simulation code that could meet the needs of multiple projects across the U.S. That is a generic groundwater flow. The user did not have to know Fortran. The user did not have to get into the code, change it, and recompile it in order to adapt it to their own field problem. But rather that would come through the general input data structure that allows the user to feed in all the boundary conditions and parameters and properties of the system in a general standard way. John then organized a meeting of all the leading groundwater modeling specialists and others that was held in Denver at the USGS Training Center, the National Training Center. And that meeting was held on January 19th, 1979. I have a memo that John wrote. He was called the Deputy Assistant Chief Hydrologist for Research at the time. And he wrote a memo on January 26th, a memo to the record describing very briefly the purpose and outcome of that meeting was. And then I have a copy of at least the first page of a memo written by Chuck Appel, who was in it's called the groundwater branch at the time. Today it's called the Office of Groundwater. He was at the meeting, and he also wrote a memo to the record describing the nature and outcome of this meeting. So basically, this meeting was to get an agreement and consensus on the need to do this and some, at least, preliminary commitment from people to contribute certain parts of it. And I think in general, the consensus was reached. There was a lot of agreement on who would take the lead on various aspects of developing the flow model. And there was even at this stage, in the late 70s, talks there was need for parameter estimation or inverse modeling to be built into it. There was need for solute transport modeling. And, it pretty well scoped out the future pretty well. The weakness was everyone who had made a commitment to follow through also had many other commitments and obligations, and progress was extremely slow, if at all. So, at least to my eye. But anyway, my perception is everyone agreed this was a great idea, and just actually getting it going and making progress on it was hard to do. One reason, and this is just speculation, is that most of these people, not all, but most of them were in the research program, and the task, very valuable and very important, was nevertheless more in the realm of development rather than research, and may have not been viewed by researchers as being as rewarding.
And up until then, the researchers were the ones who, of course, developed the code. Groundwater had no involvement other than they did disc reviews and tried to advise people and all, but they weren't developing codes or whatever, and the researchers were starting to get no credit for developing code because the opinion seemed to be that the research part of that was done, and the development was a programming thing and not worthy of getting research credit.
Most of those guys were researchers. When you asked them to actually make a model and document it the way it should be so that everybody could use it, they just balked. And nobody who was at that meeting did anything except Steve Larson, who did develop his own three-dimensional model, did use it in his work, and it did become the survey 3D model, but there was never a thorough documentation describing it and linking it to the different, and discussing the hydrology, discussing different ways that you could simulate the hydrology, and then discussing how those ways could be implemented in a numerical code, what the shortcomings of that would be, and what the dangers would be, and what the payoffs would be, and so on. That was never done.
I started that in about 1978 or 79. I can't remember when it was. But then in 1980, I left. That's where I came here because Stavros created Papadopoulos and Associates in the fall of 1979. I left in the spring of 1980. So I brought all my little codes with me. But then Mike McDonald and Arlen Harbaugh took over that project. And, you know, I think generally they adhered to the concept, but I think it became a lot more complicated.
Okay.
Certainly a lot more complicated than I had envisioned it would be. You know. So anyway, you know, they managed to carry it to fruition. They got a MODFLOW model published, and people at various levels are using it all over the place. So certainly, it certainly succeeded from that perspective. But that's kind of the history of where it came from. Because, you know, that the whole goal at the time was, you know, how do we make this compartmentalized so that people don't have to redocument everything all the time? And then I tried to follow Doug Posson's structured programming concepts. So that
everybody agreed something should be done, but the only people who were doing anything was Larson, who went almost immediately after that to work for Papadopoulos, who had started his own company.
Did people know that Larson was likely to leave?
Not until he disappeared one day. Not until he disappeared one day.
Larson was not the only modeler to leave the USGS at around this time. George Pinder had left to enter academia. Peter Trescott had retired due to illness. Stavros Papadopoulos had left to found Papadopoulos and Associates. Greg Mercer and Charlie Faust had left to found Geotrans. In addition, Doug Posson transitioned into a management position.
The only thing I had to do with MODFLOW was, I was at that big meeting. I agreed with everybody. I said, yeah, this model ought to be developed. It ought to be thoroughly documented. I said, I gave my documentation speech. Everybody was, so, but nothing happened. You know, none of the researchers would do it. I thought I heard people saying, I'll do this if you'll do that, if they were leaving. But nothing happened. Except for Larson, and he took his model with him. Anyway, both Mike, whom I had helped hire, and Arlen were doing things independently. And they weren't funded to do those things, but they were happening. I mean, they both realized that this kind of a model had to be developed, and they were working on it independently. And my contribution was to fund them to do that, to find the money to say, look, I'll pay Arlen's salary, I'll pay Mike's salary, I want them to do this, I want them to work together, I want them to make one result, so we have one model, not two. And I know they're both on the same track, and I know they've both done great things, and they'll be a great team, and blah, blah, blah. Let's do it. And then I said, you guys go and do it. And that's all I did. Basically, that is all I did. I did come in and help them with the documentation, because I do write well, and I knew they both have trouble with that. But that's really all I had to do was MODFLOW. I didn't develop the program, they did. And they did a good job, and I set some of the criteria, but we had agreed on the criteria.
Gordan talked to me and suggested that I go down to over here. So that was in 80, I think, just about 80. And while I was there, we were going to have a project where Gordan Bennett said, well, we'll have 4 people working on this thing. But all we did was kind of bumble around. I could never get people to do anything. I was not in charge of that thing by a long shot. And finally I went to Gordan and said, I'll do this project all by myself. I can do this project all by myself and I can get it done quickly. That's what I really liked doing was that. We were going to have 4 people do it. Every week we'd get together and chat about this or that or anything, but we didn't do anything. We just chatted things and it didn't work so well. So Gordan gave me the control of the whole project. Someplace in that time, Arlen Harbaugh came along, and I kind of drafted him. He was doing other things in the survey, but he also knew how to do what we were trying to do. So the two of us really came up with MODFLOW.
I became interested in trying to get a model to run, a model like on the mainframe to run on much less space if I could. I dealt with different ways to really save on storage, both in the code and in the amount of data you have to store in arrays for, to represent the problem. So that's how I kind of got involved in designing new models, is because I was trying to run on a local computer rather than having to send one job per day and wait until the next day. And I was just fascinated by these mini computers and the fact that they should really help us in the field of hydrology. They asked my boss, Don Vopel, the district chief, if as part of my already agreed upon status as an advisor, if I could work with Mike on this project. And one reason is, though, all this prototyping I was doing and the fact that I had a mini computer, and even Mike having his time-sharing terminal on the mainframe, you could enter the day, enter a subroutine, but you still either paid big money to get it compiled right away, or you might submit that overnight, or I could get these compilations through, just like that. I couldn't run a big problem. I did a lot of my simulation on a 7x7 grid, 7x7 by 3 or 4 or 5, but it was a true 3D model, but I couldn't run a big problem. But that didn't matter. We were just prototyping the structure and trying out how easy it was to add a new capability, like a new well package or something. So I assume that's one reason why they maybe chose me to help work, because I was already into it at that. So Mike and I would start working. We'd get together maybe once a month, where we both were working sort of separately. We started over from scratch several times, where we had it kind of developed that was running and all. And I said, oh no, we don't like the way this is working. Like not working again. It's not the question of getting the right answer. It was just the structure of the code. What we came up with as modules, which we called modules because of the modular model concept, not because of Fortran modules, which has been confusing over the years. But packages and procedures and all that terminology that we finally ended up with.
We didn't worry about who was doing it or who was not doing it or what was what. Someone said, hey, this is what I got today. I got this. And so it went like that. And I think it took us about 2 years to do MODFLOW. And maybe it was another half year before it actually got published.
From what previous models did you get ideas? I guess the Trescott model would be a big one.
That was one. Another really big one was the Prickett-Longquist model. You heard of that one?
Yeah, I've heard that.
And I think Trescott was trying to follow some of that style. What we liked is that the Prickett-Longquist model, really carefully documented the Fortran and the concepts with the Fortran, because at that time everybody had to change the code anyway. So it was really useful to see an explanation of the flow equation or whatever package you were working on, a river or whatever, and then see the code that added that. So the original Prickett-Longquist model had that all spelled out in it. And so they had a neat modular concept, which in a sense we kind of used in one sense. The whole MODFLOW is that way, but Prickett basically had you actually take a card deck, and then if you want to put rivers in, you take apart your card deck and stick the river cards in there. We basically say, well, whoever's programming the river puts it in there, but you don't have to pull it out again. It's just always there. But yet, if it's not being used, it's not in a way other than it might take a little memory, but it's, computationally it's having no impact.
these guys had a willingness to work on this thing and to do all the nasty, dirty programming work that was involved and solve all the different kinds of problems that could arise during the simulation. You know, anticipate them and solve them. And if the documentation is any good, it's because they cooperated when I was writing that. Because I told the chief hydrologist that I wanted to work on several unfinished projects during my remaining time in the survey. And I was given leave to do that. And then when I went to those guys, they go on and say, okay, this is good. This conforms to the way the program was written and it's fine, it's clear. Or, you know, the program isn't like that. It does this and that. Yeah, if the documentation is what made the difference. And of course, it does make a difference if you read it, and that's what you do. You know, I don't know what you'd do if you didn't. If you had the original documentation that they wrote, you had to be pretty clever to use the models. You had to know your hydrology, and you had to be able to interpret, guess what the model was saying.
Absolutely.
Yeah, I kept saying that, and the researchers always had the same answer. Well, it's not scientific work.
Do you think that's why the researchers didn't do?
Oh yeah, sure. If they had spent their time writing a documentation, then when it came with that system they had for getting ahead in the research, they had a promotion system.
Research grade evaluation.
That when it came to them, you can just imagine these 2 or 3 researchers sitting around a table deciding on somebody else's promotion. Well, all he's done is document his model. I mean, that's not research. You know. He can stay GS11 or whatever he is. Bye-bye. And they all knew that was going to happen. So why would they want to do that? That kind of thing doesn't get you anywhere.
There was a huge educational effort. I mean, they very, very intentionally had this very big educational effort. The documentation was very thorough. They did classes, I think, all over the country, really within the first couple of years. And even during development, they had users in different parts of the country.
People got their hands on it very quickly, but before we finished it, I think we probably had 500 requests for it.
Oh, really?
From around the world.
Wow.
You know, people knew it was coming and they just collected all these things. And so we started giving it out earlier.
When did you first start using MODFLOW?
I think it was in '83.
Okay.
It would have been on the very first projects.
And you said there were some bugs in it at that time?
Yeah, I was writing a program to plot hydrographs, and there was just some stupid, I think it was an indexing problem or something in writing out the binary head file that I found. It didn't affect any of the computations, and I guess no one else was trying to write post-processors because you'd think someone else would have found it. So at that time, it was still, they were considering all of us beta testing MODFLOW. They hadn't really published it. So if you found something that you thought was a bug, you documented what you thought the problem was and sent it to, I think, Arlen. And Arlen usually fixed it. I have to say, Arlen's always been totally a wonderful person.
After I left the USGS, I started my own business.
Why did you decide to leave the USGS?
Because I wanted to do things, and I didn't want to just be, I was working in the Northeast region. I was going around talking to people, and what are you doing, and how are you doing it, and why are you doing it? And I had no interest in doing that kind of stuff. I wanted to do the project. I wanted to do the projects. I like to do things and I like to end things. So that's why I stuck around, and I was in the Northeast region for probably 4 years or something like that. Yeah, that's right. As soon as we finished the first version, I think I went over to the Northeast region, and mainly because I had kids getting close to college age, and I needed to get more money to pay the tuition.
I guess you got a promotion to get more money, but then you ended up not liking what you had to do there.
Right, exactly. In a way, it was nice to go all over the country and shoot around in our Northeast region. It's about 19 states. So other people or other places had many fewer, what do you call,
water science centers?
Yeah. Langevin Water Science Center. I liked that somewhat, but it wasn't very satisfying. I could do it for a couple of years, but doing it for a long time would have been dreadful, I think.
The well-designed structure of MODFLOW made it possible for others to add new capabilities by adding new packages to MODFLOW. Here are a few of the ones added before the release of MODFLOW 2000.
Gordan had me working on the RASA projects.
Mm-hmm.
So Gordan was in charge of he was the program manager for the Regional Aquifer System Studies Analysis. And he wanted me to work on one of these projects, so that's why he had been calling me. So when I came to Carson City, I was working with Jim Harrell on the Great Basin Regional Aquifer Systems Analysis. And that's when I got involved with the Trescott three-dimensional model. Then shortly after that, a unapproved version or beta version of MODFLOW. So I started working October of 1980, and I arrived here. First year, I was working on two different areas. One was a broad regional model of the entire Great Basin, Carbonate Rock Province, we called it. It was 110,000 square miles. It went from Death Valley up to Great Salt Lake. And it was a fairly simple model. It was primarily conceptual in nature because really there wasn't that much data out there except around Salt Lake City and in Las Vegas. And then the other model that I started working on, study, was a more detailed simulation of Paradise Valley north of Winnemucca. Part of the RASA project in the Great Basin was to select a series of basins that were characteristic of several basins. So we selected a basin called Smith Creek, which was just a topographically closed basin. And then Paradise was a basin that wasn't topographically closed, and it was tributary to the Humboldt River Basin. And then there was the one in Milford, which was underdrained by limestone. There were several other basins around Dixie, Fairview Valley. It was a series of smaller basins that ended up in large things. Those kinds of things. And so we had several people working on those individual models. Jim Harrell was working on Stagecoach. I was working on Paradise. Other people were working on the other ones. And that's when I got thinking about when I started doing Paradise Valley, because it was sort of like Dry Creek, Otter Creek, in that the water comes out of the mountains, and then certain times of the year the water will go through these streams and goes across the valley. And if it's a really wet year, it'll go as a tributary into the Humboldt River. I just didn't want to assign every cell for those stream cells because there were a bunch of them, right? That's why I started working on a stream routing package. And by that time, Steve Larson had left. And so I was trying to figure out how best to do it. And then similar to that, two people, Bill Goode and Dietrich, were in the Rhode Island office. They had just finished working on a model which for the old Trescott program. I think it may have been the two-dimensional one even, where they had put lakes and streams. They were routing streams into lakes and then through a system of lakes and streams that they were just publishing. I kind of took their thoughts and ideas about the streams. I wasn't really interested in the lakes at that point. Then at the same time, Doug Maurer here in the Carson City office was working on a model of the Carson Valley, which is just south of Carson City. And he was real interested in diversions because that valley, the two large streams, the west and the east fork of the Carson, come into the valley and then get diverted off into a whole different array of canals and drainage. So that's when I started working on putting a diversion in. So those were the things that led me to developing the stream package for MODFLOW. Yeah, I was working on it in 82, 81, and I had my rudimentary. Let's see, I think the first publication of the stream routing package would be Doug Maurer's publication on Carson Valley. And I think that came out in 86. We were working on it in 82 and 83.
I guess Arlen and Mike McDonald were working on MODFLOW at the same time that you were making changes to it. So was there any coordination back and forth between you and them?
Oh, yeah. There was quite a bit of coordination going on. I mean, Mike and I spent a lot of time, not so much Arlen at the time, but it was Mike and I spent a lot of time in how this package should look for MODFLOW, because it was going to be the first package for MODFLOW. So we discussed all the details about how it should look, what format I should have it in, and things like that. What was necessary for me to document the package. I spent a lot of time going through in the documentation with Mike.
Okay, so what sort of things did you have to decide on or have to put in the code? What were your discussions with him like?
Well, we talked about that I needed to have comparison with analytical solutions,
Okay.
which I ended up doing. And then he said he wanted to make sure that it was like the river package, so that, if the flow went all the way through, it would reproduce what the river package would produce as far as leakage goes. And so that's why there's that option of no calculation of head, ICalc equals 0.
Yeah.
Okay, so that's why that's in there. The wide rectangular channel is what I was using, and so was Doug Maurer. We didn't just set a head, but he wanted me to make sure that the cells would dry up and refill again, and that I was able to simulate flows, gaining and losing, and tributary flows, and all that stuff correctly. That took some effort, but that was fine. I mean, it was important to do anyway. So the stream STR was written because I was just lazy and didn't want to assign cells to individual stream reaches, right?
Okay.
That's all that was about. And then I added the diversions for Doug because he wanted that on his model of the Carson Valley. And the subsidence package the subsidence program had to be added into the old Trescott model to do any kinds of simulation in the Central Valley. I mean, subsidence was just huge in the southern half of the Central Valley. That had to be incorporated. Then when Stan, I think that would be about 86 or something, 88, somewhere in that time frame, Stan was asking about putting the subsidence into MODFLOW, and I said, well, I've got this all. I had a rudimentary program written already for MODFLOW for the subsidence, but I was just too busy doing too many other things to get, shepherd that all the way through. So I just handed all that over to Stan, and so IBS became part of Stan, work with Stan, and then I kept working with Stan to advise him on, what could be done better. So then became IBS2. That added other features that weren't originally in the IBS1 or in the original Trescott.
So you and somebody else, Freckleton, worked on the HFB horizontal flow barrier package. What was the impetus for developing that?
Okay, I think John Freckleton was with. It's a little bit vague because in my memory, because I was, working with a number of hydrologists in districts. So I think John Freckleton was with the San Diego office. Is that correct?
No, I don't know.
It was it may be Washington. I don't remember, but there was a need to simulate narrow zones of low permeability created by faults. And at that time, there was no way to do it other than making a very fine mesh and then having some cells with low hydraulic conductivity, which would require a very dense mesh. And back in the 80s, that was computationally really expensive. So that was the reason for doing that. But and it was for a particular modeling project, but I don't remember what it was. It's either for modeling flow in basaltic aquifers in the state of Washington, or maybe it was for Southern California. I work with both offices, and I don't exactly remember which one it was.
So did you ever consider having the barriers between layers, or was that not really even needed?
I think between layers you can have, either specific layers or a vertical conductance that you can control. So I didn't think of implementing that. And the requirement for that particular modeling need was for barriers to horizontal flow, because these faults were vertical faults, so they would be low permeability zones for horizontal flow. So that was the main thing that I implemented, or the main feature of that module.
When did you start working with MODFLOW?
So I was working for Lenny in the National Research Program for the Water Resources Division of USGS. And one of the things that I did research on was the particle tracking method used in the MOC model. And I came up with some alternatives for that. But in the process of doing that, I became interested in the way that hydraulic connectivity variability was accounted for in the finite difference flow model, and stumbled across some work that Chuck Appel had done a few years earlier about the same topic, not the particle tracking, but the how do you compute the interblock transmissivities. I did a little bit of research on that. The end result of that was a USGS report about alternative methods for doing that in finite difference models. I worked that up into code that would fit into MODFLOW because MODFLOW was available at that time and was clearly the dominant groundwater flow model that was being used, and it was pretty simple to modify it to provide these alternatives.
So that was the BCF3 package, I think?
Yes.
Why did you think it was important to have these different methods of calculating the conductance?
Well, the method, the default method, the one that practically everyone uses, is harmonic mean. You can demonstrate that that's the exact solution for a one-dimensional problem where the hydraulic connectivity or transmissivity, if you want, varies abruptly at the boundaries between cells. And when I was doing the particle tracking and thinking about the particle tracking, I also had to consider where the properties change. Are they changing abruptly at the cell boundaries, or are the properties changing more gradually? And in particular, for unconfined flow, the transmissivity is the thickness of the water times the hydraulic connectivity. And clearly, the thickness of the water in reality is changing relatively smoothly, not abruptly. So it seemed to me that it was a good alternative when, for sort of more real-world situations where we have some sort of estimate of the hydraulic connectivity or the transmissivity, it's not abrupt in the real world. And so this becomes more interesting for 2- and 3-dimensional simulation. But, we showed that for a couple of examples, the standard method was the worst one to use. And so we provided a couple of alternatives that were also exact for specific problems. But in general, the case that I used, sort of a real-world case, was, sort of someone used it for a variable hydraulic connectivity with the water table on top of the model, and we showed that the default method was the worst one to use.
It was the worst one for flow or just for transport?
We evaluated that in the report only for flow conditions.
Okay.
So the velocities, specific discharge X, Y, Z, and some boundary flows.
Okay.
So just while I'm thinking about it, Richard,
Mm-hmm.
an interesting note was once I was talking to Alden Prevost about his XT3D thing.
Alden Provost, I think you mean.
Provost, right.
Yeah.
And he was noting some differences with using his method, and he was doing an unconfined flow situation, and I just happened to mention to him that he was using harmonic means, and that was the worst case if you're looking sort of at improving the accuracy of the model. For a uniform hydraulic connectivity in an unconfined situation, that was the worst method to use, and he was unaware of that. So I think that overall this method is not widely used, and maybe I haven't done such a great job convincing people that it might be beneficial in some cases.
Because I was interested in this parameter estimation stuff and the sensitivity calculations, it was very clear that the existing solvers in MODFLOW were inadequate for those calculations. And that was why I wrote, that I wanted to use a different solver. Precondition conjugate gradient was the theory that would be better for that. There was an existing PCG program in the USGS for MODFLOW, but I tried to work with it, and it had some difficulties, and so I ended up rewriting and really creating a whole new solver, and that solver I published in 1990, and I think I don't know, it might still be, I know it's still is used broadly. I don't know if it's some of the other solvers are used more now, but that solver was probably the most used solver in groundwater modeling for almost 20 years, which is kind of wild.
So you're in Arizona and Arlen's in Reston, but somehow you have to communicate the code to him for it to be included in MODFLOW. And how was that done?
When I wanted to put something in MODFLOW, how did I coordinate that with Arlen? Is that the question?
Yeah.
Yeah, Arlen was really helpful on any of these projects. So when I wanted to make something, I would basically look at the way other packages worked, and I tried to adhere strictly to the standards of MODFLOW with different procedures and routines and things like that. So a package, for example, might have a routine to allocate memory space and one to read and prepare information on RP. So, and then different ones to do different subroutines to do different procedures. So I adhered strictly to that by looking at what other packages did, and then I would develop a working version that I would modify and compile within MODFLOW, making my own changes to the main program, and then I would send it to Arlen. And of course, whatever I was doing, he was on board with, as an addition to MODFLOW. So he would make the final changes, whatever needed to be done, and put it in the official version of MODFLOW that was distributed. And if along the way I had any questions on how to do a particular thing or how to document something, he would always be willing to help. My work on MODFLOW began in the 80s. We had a major program called Russcher that was at that time headed by Ren Jen's son, the Office of Groundwater. He came to Arizona. It was perhaps as the Southwest Alluvial Basin's Russcher was being completed or had been finished. And he proposed that we have a follow-up Russcher study that looked specifically at land subsidence and aquifer compaction. So I made a proposal for that, and it was funded. And one of the parts of that was to make a subsidence package for MODFLOW. I looked at what had been done with subsidence modeling in a few other places, such as Las Vegas and Houston. Some of it was done by Dave Prudic. I can't think of the other authors at the time, but there had been some crude modifications to groundwater models. Now, I'm sure if the Houston one may have been to MODFLOW, but in essence what they did was if the head went below what we call the critical head during a time step, they would switch the storage properties to the inelastic values for the next time step. And that really wasn't a good way to do it, because MODFLOW already had built in a way to switch between water table and between confined and unconfined storage properties. It goes below the top of an aquifer, and it does that by forcing part of the storage change to that which goes with the decline up to the top of the aquifer, and then part which goes from the top of the aquifer to the ending head in the time step, and it correctly apportions those to the right storage coefficients. The process for subsidence is analogous. When your head is declining and approaching the critical head, which corresponds to the pre-consolidation stress, you want to apportion within a time step to the correct storage properties between the elastic and inelastic storage properties. So the new thing that what we call the interbed storage package for MODFLOW did was to do that correctly. And with that, you make it so the model doesn't overshoot the ending head in a particular time step. And I've written about some of that in a WRR Water Resources research paper. So we published that, I think, in the late 80s, the interbed storage package as a open file report, and then later it was published as a Techniques of Water Resource Investigations report. And just as an aside, of all the modifications I've done for MODFLOW, the one that is most widely used is called Time Variant Specified Head Package, or CHD, and that's become just a standard part of MODFLOW that anytime time there's an update, it's always put in the new version. But the reason I did that package was when I was testing the subsidence package, I had something called a ramp load test problem, which had varied in a sawtooth pattern, and I needed a way to have this boundary condition go up and down. And the one way it could be done in MODFLOW up to that point was to have a separate stress period for every little step change in head, and I needed those step changes to be done more automatically so you wouldn't be overwhelmed with input and output. So that original version of the time variant specified head package is documented as an appendix to the interbed storage package.
Model calibration has always been an issue with groundwater models. One major change to MODFLOW was the addition of calibration capabilities to MODFLOW, ultimately resulting in the release of MODFLOW 2000.
I started working with the U.S. Geological Survey in Trenton, New Jersey, and I was in the New Jersey office for 6 years. Nothing happened with the code that I had written for my PhD, but I could see people working with MODFLOW. So my thought was MODFLOW would serve as a superhighway for me to get ideas out about parameter estimation. So
MODFLOW was already published at the time you started working there.
Yeah, so I started working in New Jersey in the Trenton office in 1981. Arlen Harbaugh was there at the New Jersey office, and he was working with Mike McDonald, who was in Reston, on this brand new program. They published it in 1983 originally, and I talked to him some about it as it went. So I was well aware of MODFLOW. I thought that it was a really important thing, the way they had modularly constructed it so that people could add pieces easily. And it was just very, very well written. After I finished my PhD in 1985, so I worked full-time some before I finished, I started applying for academic positions. I applied in South Carolina and was asked to come for an interview and submit references. And I called Dick Cooley in Colorado to be a reference, and he asked if I would come work with him, if I would consider coming to work with him. And I said, well, I would think about that, but inside I said, I would give my eye because I had taken a course from him, and I'd reviewed one of his papers and marked it up, and which was really kind of humorous because in my office, here I was, marking up this thing, and people would look at it and go, I can't even read that. And you're commenting on it, So, but I guess he thought I did a good job because he offered me a job. So at that time, in terms of going to NRP, and I was hired specifically into NRP to add parameter estimation to MODFLOW. Arlen and I always got along just great. And he was interested enough in the parameter estimation that he went in talking about developing a new version of MODFLOW. He wanted it to be integrated, the parameter estimation. He thought that I had created this version called MODFLOW P, and he was basically mainstreaming that version. I had programmed in not only something called adjoint states, which he didn't want to bring in because it hadn't been used very much. It actually got used a lot later, but it hadn't been used that much in the 90s. So we made the decision not to include that in MODFLOW 2000, but we did include the other sensitivity calculation. Yeah, and we decided in 1998, Ned Banta was going to work with us and really do much more of the programming. I didn't do that much. They used a lot of my programming in MODFLOW 2000, but I didn't do the specific programming at that time. Ned Banta and Arlen did it. We decided to call it MODFLOW 2000 in 1998, and we got it done on the year. in the proposed year, so that was pretty good.
You're doing some modeling to evaluate the effects of pumpage, and at some point you got involved with modifying MODFLOW. How did that happen?
So that came as a result of another project that involved groundwater modeling, and that was not just flow, but also transport of uranium and molybdenum at the uranium mill site in the Canyon City area of Colorado. So I was using MODFLOW P in relation to that. Mary Hill's model. So I was lucky in that Mary's office was right across the hall from my office. I would bug her with questions related to MODFLOW P. But if she wasn't around and I was having a problem, I would have to go into the code and see what was going on if I couldn't figure out why something wasn't working. So on 2 or 3 different occasions, I was looking at the code and realized, oh, there's this error in the code. And so I would fix it and say, oh, great, now I can go on. So 2 or 3 times that happened. So Mary took notice. And then she said, well, we're going to be working on a new version of MODFLOW. I'm working with the Office of Groundwater. Would you like to work on it? And I said, yes. Sure, sounds great. And so that's how I got into my first job as a developer. That turned out to be MODFLOW 2000. That was a great experience. That was the big impetus for me getting into coding related to groundwater model development.
Can you tell me a little bit about what you worked on in MODFLOW 2000?
I don't remember how the work was broken out among us. Mm-hmm. I mean, certainly Arlen Harbaugh was the main architect with plenty of input from Mary for solving the sensitivity equation. So I was basically just helping to get it running and coding up the different parts. I don't remember the details, but it was just the program as a whole and working more Arlen than Mike and Mary on how to approach it and how to split out the various packages and stuff like that.
The evolution of MODFLOW continued with the addition of new packages.
Besides local grid refinement, there is the Link AMG solver.
Yeah, that was an interesting piece of work as well. And that also came out of the Death Valley work. The heterogeneity in that system was really quite complicated. And you had sometimes model cells. I want to say it was like some cells would have like 10 orders of magnitude differences in hydraulic conductivity from one cell to another. And so, as you know, for a lot of the solvers, that just wreaks havoc on them in terms of convergence. And so in again, some of the other groundwater modeling classes and courses I was taking at CU, working with Professor Hari Rajaram and some of his research group that were also doing flow and transport modeling and working in some of these systems where you had fairly complicated heterogeneity structure. They were doing a lot of stochastic simulations, but also simulations where you've got, again, non-aqueous phase liquids that are invading pore space and sort of blocking that. Obviously, you have areas of high hydraulic conductivity and then completely next to areas that are completely blocked by a non-aqueous phase liquid. And so you have these, sharp contrasts there. And so they were doing a lot of simulations with that and working with some of the different solvers and what have you. And we got turned on to this algebraic multigrid technique, which is different than the regular geometric multigrid, but shares a lot of the same principles. And so we were working on that in just sort of a research capacity, with that research group. And I said, well, why don't we try this and see if, link it to MODFLOW and what have you. So just sort of a pet project, worked on that. MODFLOW, of course, the way it's structured, it was fairly straightforward to pass in those arrays and put them into a format that was a different sort of storage, kind of a skyline storage, if you will, that AMG wanted. And so I built in between the bridge to build the hydraulic conductivity or the conductance arrays and put them into a format that AMG wanted, and then get those back out again and what have you. So I remember the first time I got it actually working. I mean, as you know, with coding, you try stuff and then you compile and then you hit run, and then usually these runs sometimes on some of these larger models, they take a while. So you go up, you get a cup of coffee or whatever and come back. And that Death Valley model, I'm trying to remember the run times on, again, some of those older workstations, but I think with the PCG, it was maybe like something like 30 minutes on a decent workstation at the time. And I remember trying it and going to the bathroom maybe and coming back. It's like, oh, darn it, this thing's already done. It must have crashed again, right? And then sure enough, I look at it and it's got the right results, And so, it was on the order of a couple of minutes, right? And so that was a real eye-opener.
So after I got my dissertation, I was friends with Frank Dagnies and Claudia Font and I guess the people working on the Yucca Mountain project. Mm-hmm. And so through them, got the contract to do work for them, and they had the idea for the hydrogeologic unit flow package at that point. They applied it to the Yucca Mountain model and would call me with problems, and I would go through, and mostly it was user input errors as it happens, right? So they're trying to do too much or didn't know exactly what they were doing, because it was very complicated to have, layers in the model that were separate from the units, and the units might span, you might have 2 units in a layer. But it seemed, like a more interesting way to look at uncertainty within a unit rather than within a model layer itself. I guess I will say that I miss working on MODFLOW. That the time doing my dissertation and afterwards working with the group on the Yucca Mountain stuff was kind of the most rewarding part of anything that I've ever done. So I was sad when the project ended, and then I would love to continue doing that kind of work.
And you mentioned SWI. You want to tell me about how that came about?
I'd been involved in variable density stuff since my dissertation, so I still monkey around with that stuff, because we did some stuff with Hsieh after I got to the USGS, while all that stuff with SWR was being developed, this side project that we did. There's this thing called saltwater intrusion meeting, SWI meeting, that happens every 2 years. So I guess the first time I went to that was in 2008. Then 2010, we went to that conference. It was in Portugal, the Azores. And Chris had known Bacher, this guy, Mark Bacher, that's a co-author on the SWI2, met him. And then, so it kind of all started, the groundwater availability study for the Florida aquifer started. And Alyssa Dousman, who at that time was in Fort Lauderdale, was the project manager for that. Plan at that time was that, well, we needed in this Florida, it would, because we were all, Alyssa and Chris and I had involvement in variable density flow modeling. We thought that was always very important. I think it obviously is for Florida. And so we thought, well, that would be something that would be important, a nice improvement over the original RASA study of the Floridan that just ignored that, said, oh, this part of the model doesn't exist because it's saltwater. That, again, trying to actually simulate the effects of variable density flow in this regional study would be good, but probably using something like Hsieh was going to be prohibitive, because the Florida aquifer goes all the way from South Carolina over to Alabama and then all the way down Florida. So it's a big model, or would be a big model. So Mark Bacher and Franz Scharz had developed the original version of SWI in MODFLOW 2000. Was never released. It was an internal code that those guys used for their work in the Netherlands. And so the idea, well, having something simple like that would be useful. And I think OGW, well, it was Dennehy's project, so I guess it came out of the groundwater availability study. It's like, we're going to need some technique, some way to represent freshwater, saltwater, variable density flow in some fashion, but simply. So we cooked up this plan that we should actually implement SWI so that we could use it for the Floridan and make it an official USGS package. And everybody was in agreement, right? Bacher wanted to do it, Franz Scharz wanted to do it, Alyssa wanted it for the project, so that became a component of the project. We ended up developing SWI, or SWI2, as it would be called.
In addition to new packages added to MODFLOW, variants of MODFLOW were created as separate programs. This was generally because the changes required to support these new capabilities were too extensive to be easily incorporated into the existing MODFLOW framework.
My other contribution of any significance was that we made a version of MOC that was 3D that used MODFLOW for the solution of for the flow velocity, specific discharges. So I was the initial program coder, for converting MOC into MOC 3D. And instead of solving it, having its own groundwater flow solution, it used MODFLOW for the groundwater flow solution.
Yeah, I remember you've talked about that one time, and I think you complained about it not being published in a timely manner. You want to
comment about
Yeah, I think by the time we published it, MT3D was out, and it included the method of characteristics and other solution methods, and it was, it had already established itself as a very useful tool. So we kind of missed the window of opportunity on that, I think.
John Pence called me up from the Corps of Engineers in Davis and wanted help with a model that he was working on Tooele. So I made arrangements to work with the Corps of Engineers on developing a pump and treat model for the Tooele Army Depot in Utah. And so I was working down there, and then with conversations at the Corps of Engineers, they were talking about how hard would it be to connect a rainfall runoff model to MODFLOW. So in the summer of 1994, I spent the summer over in Davis, California, doing research on how one would want to connect a rainfall runoff model to MODFLOW. And so I developed this whole scheme of how to do that, right, that summer. And started talking to various people about how to get it funded. That took several years. And then in the meantime, Lenny called me up and wanted to put solute transport into STR, right, because he had done it in the lake package. That was about 2000. And so the Office of Groundwater, I said, well, that'd be fine, Lenny, except I want to really change the streamflow routing package to help me with this design that I was working on for this rainfall runoff model. And I wanted to add different options so that one could look at not just a wide rectangular channel, but a cross-sectional area, and lookup tables if you wanted to. And I also wanted to have a better connection with doing priorities for streamflow diversion. And even though I didn't get to that part, that was in the intent. So when Lenny called me, the Office of Groundwater said, sure. So I started redesigning the whole streamflow package into what became SFR1. Then when we got permission to start working on the other parts of the package that needed to be done to connect the rainfall runoff model to the groundwater flow model, and Rich came over as a graduate student.
That's Rich Niswonger?
Yeah, Rich Niswonger. So he began helping me with developing the coding for what became UZF. And we put UZF into the stream package to begin with. I thought that would be easier than making it model-wide to start with. And so our test was to put unsaturated flow beneath the stream channels to see how it worked. So that evolved into SFR2, and then once we proved that was feasible and workable, and we could do that, then we decided to do it over the entire domain, right? Didn't matter whether you were underneath a lake or underneath the stream or just at the end. And that became the UZF1 package. That was all from that original research that I had done back in 1994, where I had identified certain analytical equations that would work well for modeling this unsaturated flow without having to go into the full 3D Richards equation. I was trying to find economy as much as I possibly could, because people were doing these large 3D Richards equations, but it seemed kind of odd to me. So I was still working on how can I still simulate this, but make it economically or computer-wise feasible.
I guess the main advantage of not using the full Richards equation is that it goes a lot faster and doesn't use as much memory.
Yeah, and for most groundwater problems, I went to this Roger Smith equation that does, it's a Lagrangian approach to tracking packets of water as opposed to having a fixed space. And that seemed very reasonable because you could end up having like 20 or 30 or 40 of these little packets that you were tracking. And sometimes, and at other times, you might only have one or two packets. So it seemed like a very efficient way, instead of having to divide the world up into so many vertical cells, that it seemed like an efficient way of doing it. And the biggest problem we had was how to connect that to the water table, but we were able to resolve that reasonably well.
What was the problem with connecting it to the water table?
Well, the water table's rising and this stuff is coming down. How do you incorporate that, right? So the water packets are coming down and the groundwater levels are coming up.
Mm-hmm.
We had to come up with a scheme as to how to capture that water that was coming down. Where would it be, right? So that was the big thing. And that what happens if you're not careful, and that was part of the numerical instabilities, was that if this you essentially had a saturated column coming down all the way down in UVF, right? And
Mm-hmm.
this groundwater table is rising and it hits that saturated zone. You could pop it up to land surface in a hurry.
Okay.
So,
Well, I mean, it's a big change. But I guess that would make the solution unstable, but it could be actually real, right?
yeah, right. It was actually real, but we had to come up with keeping it stable right at the same time.
I see.
So Rich came up with some rather ingenious ways of doing that. Like I said, the guy's amazing. So that was UZF. And then once we had UZF pretty much dialed in, that's when Bill Alley said, okay, we're going to connect PRMS. I wanted to connect the Corps of Engineers hydrologic modeling system, but Bill said no. If I was going to get funding from the Geological Survey,
Mm-hmm.
it had to be PRMS MODFLOW. And so that's when Rich and I started working with Steve Regan and Steve Marks. We spent a lot of time, and George Leesley was still working at that time. And that was about 2004, I think, that we got the permission to start really working on what came known as GFFlow. And Paul was the person that was kind of overseeing our progress, because he knows that Bill knew that we were a bunch of goofy scientists getting lost.
That would be Paul Barlow?
That was Paul Barlow and Bill Alley. So Bill was very cognizant that I tend to get lost in details, and so it was very nice to have Paul spearheading everything that was going on. What transpired in all of this, they decided to use Randy Hunt's Trout Lake study as the first, besides Spaceship, as a first real groundwater kind of study, right? That had for GFFlow, but it had lake, and the lake package had to completely be redone because it didn't keep track of budget once the lake dried up. And so it was not very stable. And so Rich and I had to come up with ways of making the lake disappear while keeping a budget and then allowing it to form again.
Jim Constance introduced me to Dave Prudic. And Dave Prudic, he worked for the Nevada Water Science Center, and he had done development work for MODFLOW. Notably, he developed a streamflow routing package for MODFLOW. And so when I came on as a student at the Nevada Water Science Center, I worked under Dave Prudic. And that was right at the time when Dave was thinking about integrating like watershed models with MODFLOW. And he was also kind of developing kind of different, more robust numerical methods for the streamflow routing package. So he was kind of midway through developing the SFR package. So he had developed the STR, and then he was developing the SFR package. And one of the things that he was thinking about was how to integrate a watershed model to MODFLOW, and then obviously that led us to, okay, well, how do we represent unsaturated flow between the shallow surface hydrology down to the deeper aquifer system? And so we started working on the unsaturated zone flow package. And then through that work, Bill Alley reached out to us and asked us to join this meeting at Federal Center in Colorado. And different people from different parts of the USGS came to that meeting. And the goal of that meeting was to develop a blueprint for, building an integrated surface water, groundwater hydrology model that would basically extend the capabilities of MODFLOW to include surface hydrologic processes, so runoff processes, surface water-ground interaction, and evapotranspiration, soil zone processes. And so there were a lot of different groups that presented, different approaches at that meeting. And I think generally the consensus was that we wanted to develop something that was not as computationally demanding as using a 3D Richards equation approach. And so that was why we got funding to integrate PRMS, precipitation runoff modeling system, to MODFLOW. And then we started collaborating with folks from the Water Mission area in Colorado, notably Steve Markstrom, Steve Regan, George Leesley, Lauren Hsieh. And then I got funding to work on MODFLOW.
we updated the streamflow routing package in ways that made it more robust. And then we developed the unsaturated zone flow package, which enabled us that kind of was the coupling mechanism between PRMS and MODFLOW. So then we released those as packages. And then we updated the Leake package so that it would be more stable and mass conservative so that we could include that as a part of the coupling with PRMS. And then we made some modifications to other MODFLOW packages and released those as separate MODFLOW packages. And then finally, that led to the development of GSFlow. I'll start with my collaboration with Sorab, Panday, and Mudabu Ibaraki. So I was trying to develop a more robust solution for MODFLOW for wetting and drying. And I wanted to use the Newton-Raphson method because my experience with, I had solved the St. Fanon equations, and Newton-Raphson for that problem was much more robust than Picard. So I thought, well, maybe Newton-Raphson would be useful for MODFLOW and adding greater robustness. And so I presented that work that I was applying Newton-Raphson to MODFLOW. And Sorab Panday came up and talked to me, and we were like, he had done applied Newton-Raphson in MODFLOW Surfact, and he's like, oh, I want to work on this with you. So we collaborated, and then similarly with Mudamu, he had been developing the ChiMD solver, which was using kind of the latest technology in linear solution, matrix solution problems. And so we all worked together and we developed MODFLOW Newt. Sorab also wanted to develop an unstructured grid version of MODFLOW using the same technology that we used in MODFLOW Newt. We collaborated to use those methods that we used in MODFLOW Newt and to bring those into MODFLOW USG. It was kind of almost simultaneous that I was developing MODFLOW Newt coding, he was developing MODFLOW USG, things that I was learning in MODFLOW Newt. I would talk to him, he would incorporate those in USG, and then vice versa. So we were developing those two separate codes and learning from each other and kind of incorporating what we learned in that collaboration. So that was my connection to MODFLOW USG. And then for MODFLOW 6, Chris Langevin and Joe Hughes, they wanted to also use Newton-Raphson and get that added robustness that was provided in MODFLOW 6 as an additional option. And then they also wanted unstructured grid capabilities and integrated finite difference technique that was used in MODFLOW USG. And so they reached out to both Sorab and I, and then we collaborated with them. Mostly I provided consultation on how to implement the Newton-Raphson, and Sorab consulted in implementing the unstructured grid. And then we also incorporated, so I developed the UZF package version for MODFLOW 6, and then Joe was working on developing the SFR package for MODFLOW 6. So we were all kind of discussing and meeting regularly and collaborating on kind of how to implement and refactor the packages that we developed for MODFLOW Newt and MODFLOW 2005, including UZF, SFR, the Leake package, and then MNW. So Joe did a lot of the work for SFR and Leake and MNW for MODFLOW 6. I worked mostly on UZF, and then we talked a lot about other improvements that we'd like to see in MODFLOW 6. And of course, Chris was working on kind of the overall structure, the multi-model structure for MODFLOW 6. So we were all kind of working a lot together on that. And then Alden Provost, he worked in Ned Banta as well, adding additional capabilities to MODFLOW 6. And then that was when Alden implemented kind of it's like a new updated version for ghost node correction for unstructured grids. What's the name of that process? It's
I know what you mean, but I don't remember what it's called offhand.
Yeah, that was kind of Alden's big contribution at the time. So that's kind of all of our kind of working together and contributing to MODFLOW 6.
So the first project was
trying to quantify how much fresh water was flowing into Biscayne Bay, marine estuary. I was taking over for somebody who was leaving the survey.
This is still with MODFLOW 88, I assume.
This was with HST3D. It was variable density, so it was simulating flow and transport because the saltwater interface was important there. So I started working on this project, and very shortly into this project, I met this guy named Weijing Guo, who was working for, I think, Mismer and Associates at the time. It was a consulting firm there. So Weijing had recently put together MODFLOW 88 and MT3D to simulate variable density flow and transport. So he had worked to add all the density terms, calculating density from concentration, and adding buoyancy terms to MODFLOW 88 to simulate variable density flow and transport. He did this with Gordan Bennett. And so Weijing gave me a copy of this program and said, I met him at a meeting, and he said, hey, and I said I had HST3D was pretty complicated to use. And he said, give this program a shot. And from MODFLOW background and MT3D, I knew it well from my dissertation work. And so I started working with it right away, building data sets to simulate flow in Miami and how much fresh water was flowing to Biscayne Bay. And it worked really well. And I had just shown up there in Miami, and I said, this looks really promising. I would like to pursue this. The USGS gave me full support. They said, you know what, we would really like you to work with Weijing and use it for this project. And I talked to Weijing, and he was like, well, let's make this CWAT a USGS program. I got full support from the USGS to work with Weijing, not only to apply CWAT to this particular project, but also to make CWAT a USGS program that we released and distributed. I was really fortunate to be able to meet and work with Gordan Bennett. I went to his house with Weijing a couple of times, and we worked on the manual, and ultimately we published CWAT as a USGS program. So yeah, it was a great experience.
Then, you didn't stop there. What happened next?
So CWAT just became a really critical part of everything we were doing in South Florida at the time. So while I was there, the projects just exploded. We had projects doing aquifer storage and recovery, injecting fresh water into saltwater aquifers. We had modeling projects looking at Everglades restoration, looking at salinity transport, both in surface water and groundwater. We had saltwater intrusion projects. Ultimately, we had so much work, I was able to hire many different people, Lindsay Brakefield, Alyssa Dousman, Melinda Lohman, all these people in South Florida. And we were able to build a pretty sizable group of like 10 people working and applying CWAT to these problems in South Florida.
Oh, was it the availability of CWAT that was the driving factor, or was it that these problems were there and they would have been addressed with something?
I think it was both. These projects were coming up fast, and we in the USGS in Miami we found our niche there, and we had these capabilities that nobody else had. And CWAT just started becoming very popular. We were teaching classes to the South Florida Water Management District, to the Army Corps, and even around the world, we started teaching CWAT classes. It started taking off. We had more work than we could do.
And that continued until?
So that continued until about, I think it was 2009 or 10. At one point, I was talking to Paul Barlow, and we were talking about CWAT, and the Office of Groundwater had been funding some development of CWAT to, just to help promote it. And something came up, and Paul said, would you ever consider coming to Reston to work for the Office of Groundwater? Mm-hmm. And Arlen Harbaugh was kind of winding down his career, and they were looking for somebody to take MODFLOW in the Office of Groundwater and carry it forward. I had a couple of conversations with Bill Alley, and he asked if I would come up and take a position with the Office of Groundwater? And I said, absolutely. And so we packed up ultimately from Florida and moved to Reston, where I began working with Arlen and Tom Riley and Jim LeBaugh and Bill Cunningham and everybody in the Office of Groundwater to transition MODFLOW essentially from Arlen as the caretaker to me as the caretaker.
There was work ongoing with Department of Energy in Yucca Mountain and issues with flow and transport there. And of course, there was this Death Valley regional scale model, but there was interest in building these local scale models in some of those areas. I had in Tisa's class, coincidentally, we were for our project, worked on some flow and transport model where we had a local scale model that was given to us by a consultant. They generated the boundary conditions for us, and then we had to work with this model. And our group in particular, we just had a really heck of a time trying to work with this model, and we realized later on it's because the boundary conditions just really weren't that great that were given to us. But when you impose these constant head boundary conditions, they just have so much control over what happens. And when I was mentioning earlier that Mary kept asking me, hey, you want to do a PhD? I've got some ideas, and she had these various ideas of things to explore, and that was one of them with these local scale, building these local scale models and what they were doing. And I latched onto that right away because I said, hey, I worked on something like that, and we had a horrible time with it, and I there's got to be a better way to do that than sort of this, the way that was conventionally sort of thrust upon, just put constant head boundaries around the whole thing and go for it. And so I said, and then she had me hooked after that. So that was sort of the precursor, I guess, to LGR, doing the local grid refinement. And there was the other codes, Stan Leake had a really nice code for doing that as well. But we refer to that as sort of this one-way coupling. You do it once and that's it. And if you don't get it right that first time, you can just really have a heck of a time with getting that model to work out. And so, we had this idea of, okay, now you iterate back and forth on the boundary conditions and trying to get agreement with both flow and head. So essentially conserving mass and energy, if you will, on the boundaries.
So you started working on farm process and maybe I guess other parts of what became MODFLOW OM as well. Yeah. So what parts did you primarily contribute to, do you think?
Actually, fortunately, it's so long ago, and back then I was mostly in a manic code state where I was just programming constantly. The only ones that come to mind are I had adapted the solvers so that they can be read by stress period. Mm-hmm. So traditionally you would set up a solver like the preconjugate gradient, you'd specify its convergence information. And so I had modified it so that it would either do one set of convergence at the beginning, and then you would read it you could read it every stress period to kind of change the number of iterations for stress periods you may know it has difficulty solving. Some other things I had added in, kind of something that was analogous to a time series file. Mm-hmm. And that was attached to like SFR and the general head boundary. I had also wrote something called an expression parser. Mm-hmm. And so that enabled people to feed in a custom expression to something like the general head boundary. And so what was common for a lot of models in California is that they would set up the general head boundary condition to represent a sea level, but they would not be doing a density dependent model. They would just be doing a freshwater equivalent. Mm-hmm. And so you could pipe in an expression for every cell based on its location, and it would adjust what you specified as like a sea level gauge, and then it would make it into a freshwater equivalent head. Mm-hmm. So that you could do particle tracking to see where the seawater intrusion occurred. And then improvements to the farm process. A lot of what I did was optimizing it, and I want to say when I first started coding to when it was published, I reduced the speed by about 60 to 70%. So like a 10-minute model started running in about 3 minutes. And that was just largely just reordering loops, vectorizing some of the arrays, and so forth.
One of these things I didn't know about till a long time later, and that was the Colorado Decision Support System, I think, CDSS.
Yeah.
What was the reason for making that?
Well, our office had a working relationship to a certain extent with the Colorado state government. Their groundwater They're part of their, I don't remember what they call it, how they're organized and what they call it, but they had people who would do modeling and stuff for groundwater modeling. And they came to me and wanted to be able to kind of look at these parts of the groundwater process, like say the well process was one in particular, well package, where they'd say, well, we'd like to really be able to look at water balance kind of with a higher degree of detail than just all the wells lumped together. And they wanted to be able to, say, look at just wells either of a different type, whether they're domestic wells or public supply wells, or whether they're wells in different aquifers, because they're mostly what they're interested in is the Denver Basin, and the state identifies 6 different aquifers in the Denver Basin. So they had an interest in being able to look at and lump together the wells in a way that was helpful for their analyses. Not just wells, I think, but probably also drains and streams, stuff like that. That was kind of interesting because to do that, what the approach that we came up with was to use some capabilities of Fortran. Before, there was an object-oriented version of Fortran, but it was kind of, it's kind of like the developers of Fortran were very slowly kind of getting away from the original non-object-oriented structure that it had for a long time. And it took them a long time, as I'm sure you know, to get to where it's fully object-oriented. So this was kind of like an intermediate step that would allow you to access memory in chunks.
I finished my PhD. I started a job in Virginia, and basically with Peter Huyakon at Hydrogeologic. And since I always had that bent of doing coding, I kind of made sure I got into the coding environment at Hydrogeologic. And then when we started working with MODFLOW more, and I started doing coding within MODFLOW itself then. So that's how I started getting into coding within MODFLOW. So this was, I'd say 91 or so, and we were working on a project, and there were some issues with wetting and drying and re-wetting, the MODFLOW re-wetting issues. So what we did originally was, at Hydrogeologic, was to try and overcome that with this pseudo soil functions, which are essentially looking at unsaturated flow, but then making vertical equilibrium soil functions. So your soil functions don't have capillarity, and then integrating that over the grid block. So that is something that worked, and it worked very well in MODFLOW Surfact. Then we continued developing things within MODFLOW framework, which included contaminant transport. It included surface water connections, and pretty much since MODFLOW is such a standard, everyone was using it. We just started building capabilities of doing all these other things within MODFLOW itself. Things like also the well capability. So the MNW package, which is in MODFLOW, we kind of did something similar like that. But again, at that time, numerically, we were different from MODFLOW. In that the MODFLOW was always a structured, it had structured solvers, so it was always a structured code. Even then, we started using these unstructured solvers, and that is when we started doing full coupling instead of this iterative coupling. And so that really took off a lot, really helped with a lot of the MODFLOW things. So then when I left Hydrogeologic, so that was all proprietary, so I couldn't touch anything. In fact, right now, our company has bought MODFLOW Surfact licenses. We have to pay for it, we just get the executable, I can't do anything. So I had to start off, I had to do something. So it was literally, Richard, I started from scratch, and I decided at that time, well, 2 things. One is that it's a technology transfer. We were doing certain things which were so much more advanced, and I have some capabilities which I thought, it's time to get out, as technology transfer. And the other thing was that I wanted it to be open source, public domain. So if I ever left any company, I don't have to leave all my stuff behind. So So I'm not starting from scratch 10, 15 years later. So I decided I'll do open source public domain coding.
Okay.
And actually it started with Jim Rumbaugh coming to me and saying, Sorab, can you write finite element code for me? And I said no and no. I'm not going to do finite element code because that's outdated. There are better schemes, and what we do now in MODFLOW USG, MODFLOW 6, those are the schemes, pretty much those are the schemes we suppose we should be using for fluid mechanics at least. Finite elements have their own problems. So no to finite elements to Jim and no to doing it for him. I said no, it'll be open source public domain. So that's how it started. And I approached Chris and Rich actually, Niswonger. Said, see, this is what I'm doing, and I don't have all the budgets and the capacity, and if you want to join with me, that'll be great, it'll be perfect collaboration. It'll be open source. It's all good. That's how I told Chris. And really, even to this day, Richard, it's all good. It's like, I'm doing this. You want it, take it. You don't want it, don't take it. It's fine, and that's when it's that way, it's really all good, There is no conflict at all. So I've been continuing to do that since then. So I started with MODFLOW USG. When Rich and Chris first came and looked at what we were doing, I paid my respects to Arlen. If you remember, I'd come to the office and Arlen asked me, what are you going to be doing? How are you going to be doing this? And I said, this is what I've been. And actually Arlen approved of what I was doing also, so that was good. And so I just continued developing MODFLOW USG. Then MODFLOW USG comes to a corner, in a way. Finally, MODFLOW itself, just building on MODFLOW comes to a corner. You get stuck in a corner and you have to do things to get yourself out. So that is, I think, Chris and Joe are the ones who came up with this framework, MODFLOW 6 thing, and that is awesome. So now you can start plugging. It opens you out. That's what MODFLOW 6 is doing.
One of the biggest changes to MODFLOW was the support for unstructured grids in MODFLOW USG.
So when you came up to start taking over for Arlen, did you already have in mind a new version of MODFLOW with more, with the object-oriented stuff that's now in MODFLOW 6?
No way. Not at all. The one thing that I did come interested in was unstructured grids. And so shortly after I arrived in Virginia, I connected with Sorab Panday. I connected with him because of Jim Rumbaugh. And I had always known Jim Rumbaugh. I'd used groundwater vistas. And I was talking with Jim about unstructured grids. And Joe and I had been talking about unstructured grids in Florida. And Jim Rumbaugh said, you know what, you should contact Sorab because he's been working on MODFLOW USG and it sounds like something that you guys would connect on. Sorab had an office in Herndon, Virginia, very close to the USGS office. I reached out to Sorab and we struck up a close working relationship and friendship. Like with CWAT, I worked with Sorab. Ultimately, Sorab was the main architect, but to make MODFLOW USG a USGS product, and it was something that I did through the Office of Groundwater. That's how that MODFLOW USG came about in the USGS. So that was well before MODFLOW 6 was ever conceived.
So tell me about the development of MODFLOW 6. I'm sorry, MODFLOW USG. I'd sort of forgotten about that.
So MODFLOW USG was just a big hit. Right? Sorab and I had weekly meetings. We talked about how to document MODFLOW USG, how to try to preserve MODFLOW in it, but yet make it fully unstructured. And we talked about how to organize the internal arrays most efficiently and write the output, come up with new, all the UBudSave B or UBudSave UB, all these writers. We worked pretty closely on all that. But we worked most closely on putting MODFLOW USG through its paces. For example, we found ghost node corrections. we found out, hey, if you put together these grids, you're going to get some errors in them. And it was through testing, MODFLOW USG with analytical solutions and variations on it that we came up with the ghost node correction package. And Sorab was a master, and he would implement that, and I would test it. Then we wrote the documentation for MODFLOW USG, which I think is a really good documentation. It's pretty thorough. We talk about how you do unstructured grids in a MODFLOW framework and ghost node corrections, and the Newton-Raphson formulation, and how do we solve unstructured matrices and asymmetric matrices. These are all things that we tried to document in MODFLOW USG documentation. One of the things that struck me was the MODFLOW USG document. We put it through review. I remember you were a reviewer on it. You had a comment. I think about it to this day. I don't remember the exact words, but it was something about a horse. If you ask somebody who was riding horses what they would want.
Oh, that's from Ford.
Yeah.
So if you ask, if I asked people what they wanted, they would have said they wanted a better horse.
A better horse. When really what they needed was a car.
Mm-hmm.
Yeah. And so I remember that comment, and I remember working with Sorab quite a bit, and it was really, we were shoehorning. Mm-hmm. We were shoehorning new capability into a MODFLOW ecosystem, which wasn't designed for it. This wasn't me saying we need something different. This was all of us. This was Arlen. Mm-hmm. This was Dave Pollock. This was Joe and Sorab and Rich. And it was us just saying, you know what? We're really moving things forward now with unstructured grids, with Newton, with SFR and Leake communicating, and all these things that were much more complicated than MODFLOW was originally designed to handle. And we said, we need a new way to deal with this, and we should design something from the bottom up. That wasn't one meeting, that wasn't 5 meetings, that was the Office of Groundwater saying, we're going to intentionally come up with a new version of MODFLOW that can do what we need it to do for the next decade or two. At that point, Joe had started receiving quite a bit of funding from the USGS, and I think we started in 2013, which was about the same time MODFLOW USG was released. We started prototyping the first version of MODFLOW 6 in Python, just trying to wire up the ability to solve multiple models and multiple packages with a single linear solver, and relieving that restriction in MODFLOW, which was essentially the solver solved a single MODFLOW grid. Mm-hmm. And we wanted to try to elevate that. So a solver could solve multiple packages, multiple models. And so we prototyped that in Python.
An interesting thing is how Alden Provost got involved in MODFLOW 6 is one of the components of MODFLOW 6 is can do unstructured grids. We went and talked to Alden, Chris, and I, because we knew we were going to have to deal with dispersion for transport models. Sorab had some approaches that were interpolating off of a ellipsoid to come up with the dispersion components in the direction of the cell phases. It's probably okay, but it wasn't a rigorous kind of approach to dealing with that. We started having this discussion. Him as well, we're going to have to deal with dispersion on these unstructured grids. The traditional approach of dealing with dispersion in rectilinear grids could be adapted and used in terms for these unstructured. Alden, say, goes away for a month, some period of time. But then he comes back with XT3D. Nobody really does it like this. It's basically interpolator, and we're like, oh, yeah, that sounds great. It has all these tests, he's doing all these plots, showing all this stuff, doing what Alden does when he talks about dispersion, using his arms, and he doesn't use his legs, but in the 3 directions for the ellipsoid. And so we're like, oh yeah, that's great. Really interesting, really interesting. And so it's like, okay, we can move forward. And I don't know that it exactly went like this, but I'll say that it is because it was something along these lines. Because at some point in time, it comes back, well, right? Well, we could do 3D anisotropy, right? The same method. right? Again, the task was dispersion, but then we get 3D anisotropy for the flow solution. And then ultimately come out to find we had something for basically where you have the perpendicular bisector, where you violate the CVFD constraints, where you don't have perpendicular bisectors, you get these weird oscillations. And so we had ghost nodes, which was, I think Jesse Dickinson was involved in developing, and Steffen Mehl had ghost nodes as part of LGR. So it was a known commodity. But then come to find out that XT3D basically can give you the same as ghost nodes, that you don't have to define the ghost nodes, and actually is better, right? Because it's more than just a single kind of interpolation point. So again, from that discussion of, hey, Alden, can we do dispersion on non-rectilinear grids? We get that. Plus, we get XT3 3D anisotropy on unstructured and also structured grids. And we also get a replacement for ghost nodes that actually is better than ghost nodes, and there's no required user intervention. So from that one conversation with Alden about one specific thing, we have 3 significant contributions to MODFLOW 6 and numerical simulations beyond MODFLOW, if people were so inclined to use them. So it was just amazing what Alden could do. That's nothing that I would say nothing I could have ever done. Chris would probably say that's something he couldn't have done. He's had an enormous impact on MODFLOW 6. He's a real treasure at the USGS. Did Chris tell you the story of why it's called MODFLOW 6?
No, he did not.
No? Okay. Well, I can tell you now or later.
Tell me now.
Well, so it was just this issue. We're always fighting against time. We would call it 2017. But so that was the first pain. And then the second was we would occasionally hear from people, again, these snide comments. MODFLOW 2005, right? It's 2015. It's so old. So the whole idea of putting that year on it could make it so like, oh my God, this thing is very old, when it never was. I mean, Arlen released versions at least every year. Maybe it was slightly longer, but again, it's like, sure, it's 2005, but this is 2005.11, which means it's been updated. There's new features for that whole time. So the idea was to basically kind of remove that year attachment to it, just so that, again, that maybe it would become clear that this, just because it's the 6th version, right, really, that just means that basically that all of these versions that would be part of this 6, for the most part, should be consistent and ideally backward compatible to whatever degree is possible. But this is the framework or the design that we're working with at this point, not that the code itself is aged. So that is kind of the history behind it. And also the embarrassment that 2015 was not finished in 2015.
Occasionally, not very often, I hear people say, ever going to write MODFLOW in some other language of the day? I guess you might have gotten those questions too.
Yeah.
Do you think that's ever going to happen? Anytime? Well, okay. Ever is a long time. Is that anything on your horizon right now?
I would say we're all fully invested in what we have right now, which is Fortran compiled code with a Python ecosystem surrounding it. We, for the near term, meaning the next probably 2 to 5 years, we don't see that changing. Though certainly as our needs and ambitions become more sophisticated, we may need to consider alternatives. But I would say our ability to compile Fortran so easily and reliably on multiple operating systems and with available compilers and compiling into executables that are pretty transferable and reliable is something that's been a big benefit, and we're not looking to change that anytime soon. But we absolutely are very in touch with what the most popular programming languages are, the benefits and drawbacks for all of them, and whether we should or when we should change to something else.
Is there anything else you think people would want to know about how MODFLOW 6 was developed?
Well, I don't know whether it's interesting or not. We had this, I think it somewhat haunts us to this day, is we had this whole discussion of what should we, it was going to be a complete rewrite.
Mm-hmm.
What language should we rewrite it in? There was a lot of back and forth, and so ultimately it was, the two choices were Fortran or C++. That's what was being contemplated. Some people were open to C++. I was probably the most adamant advocate for it, but we all kind of came to the consensus that okay, we're going to do it in Fortran. I guess we had explored enough object-oriented Fortran at that point that we could say, okay, we can go this route. And maybe this was in 2013. It probably was in 2013, actually, where we had this discussion. Because the idea was, well, we keep it in Fortran because the people that have contributed to MODFLOW in the past, that are familiar with Fortran, could still contribute. We wanted to still make it an accessible code for people with Fortran experience, and past contributors could contribute to as well. It was a heated discussion, or like I said, I think I was more on the side of we should do it in something like C++. The whole object-oriented nature of the thing, it was different for for Sorab and for Rich. I guess for those two, Ned was used to object-oriented programming, and Chris as well, because we were like heavily into Python at that time. So all of these things were up for debate, and then ultimately we decided on Fortran, again, to try and facilitate other people contributing to the code, which is probably good, but it ends up, that's the one thing. People will always beat a code over the head over something. It's like, oh, it's written in Fortran. Nobody knows how to program in Fortran, and it's so old. It's like, you can never win, but where would we be now? Probably someone would beat us on the head. Well, it shouldn't be in C++. It should be in language XYZ, right? So maybe you never win these arguments. Anyway, so that was an interesting debate. So it's not like we just did it because we knew Fortran.
Okay.
People probably don't realize that. Again, it was a serious topic of discussion.
So I know a little bit about what you've done, but it's really hard for me to tell exactly who did what. Could you sort of summarize what sort of things you have been working on?
Yeah, and let me start by saying that I think it's for anyone hard to say who did what, because we do so much together, fortunately, because I think that the quality of software is highly determined in such a complex framework as MODFLOW 6 is. Mm-hmm. It's highly determined by the amount of collaboration between its developers. Okay. And so we typically talk about our ideas or our designs and review them among each other before we start coding at all. One of the first things that you might have heard of this week that I worked on, and I worked on it a lot actually, was the API, the Application Programming Interface to MODFLOW 6. It was a very practical reason to start with that, because the Dutch national model used that a concept, like use the coupling to MODFLOW 2005. Well, basically the coupling is part of that national model to couple the unsaturated zone to the groundwater. But we wanted to upgrade to MODFLOW 6. And at Deltaris, it's been a good practice to use a standard called BMI. It's not really a standard, but known as BMI. It's from CSDMS here in Colorado. To use that to make a model interoperable without being too invasive, basically, into the model code. So we wanted to follow that practice, and we've developed such an application programming interface on MODFLOW 6. And I guess that will be the first major contribution. But it came during, it started as a side project, because the piece of work that we're basically going for was the parallelization of MODFLOW at that time already, which was delayed because of our work on the API. And I think we're happy with that. I mean, it's been quite successful already, and it's only just starting. But the parallelization of MODFLOW 6 that Jarno, who I mentioned earlier, started at first, is something I took over, and the idea was to have that in the MODFLOW 6 development version to be released, the official USGS release.
Okay.
So, and that's something we're actually still working on. I'm really impressed by, and I'm really happy with the way that MODFLOW 6 has been thought of, designed, conceived, and developed, and the modern approach and open mind that Chris Langevin and Joe Hughes, Alden Provost, maybe a little bit less on the software engineering aspect, but a lot on the numerical concepts, that they've shown me that how they put that into that framework. And I'm just really glad that I can work with a software framework that has so much potential. That's just beginning to become even greater, instead of what happens with software projects. They come to a standstill after too much development because it's just increasingly harder to add anything to it. Whereas this has been designed from the beginning as something that's extendable and stable, sustainable, well documented, well tested. All these things that I find are lacking for a lot of other codes.
Part of the success of MODFLOW can be attributed to the development of support tools for it. These were mostly developed outside the USGS as commercial products. A few, such as Model Viewer, FlowPy, and ModelMuse, were developed by the USGS or with substantial USGS involvement.
Now, I saw that you were also a co-author on the linked MT3D-MS package in 2001. Now, do you remember that, and what was your involvement with that?
Junmao Zhang was a visiting professor at Stanford for about 6 months, and he arranged it so that he would spend maybe 2 days a week at the USGS in Menlo Park. So I set up an office for him, so he would come to Menlo Park for a couple of days, and then he spent the rest of the week at Stanford. And so my involvement with him was really including MT3D-MS into Model Viewer. And to do that, you have to read data from the link module. So that was my involvement, not really with any of the number crunching within MT3D-MS, but how to interface it with Model Viewer so that the simulated concentrations can be displayed in Model Viewer. So when you look at that report, there's a section of that about using Model Viewer with MT3D-MS, and that was my contribution.
Okay. Do you want to talk about your work on Model Viewer?
Sure. Sometime I don't exactly remember when, maybe in the 90s, I became aware of a set of libraries written in C++ called VTK, which stands for Visualization Toolkit. And it was developed by 3 developers who used to work for General Electric Medical Systems. I don't know if that's the official name of the company, in upstate New York around Albany. And that company was developing 3D visualization for medical purposes, for like brain scans and things like that. And they wrote this library as an open source software and have the code available for anybody to use. And then soon after that, they left GE and created their own company. I think it's called Kitware, and further developing applications for various types of visualizations. And I realized that this set of tools was really useful for model visualization. So I started developing code to use this toolkit for visualization. And in fact, at the beginning, the toolkit only worked with, if you have, like, let's say a mesh, the toolkit would only work with values at nodes, that is at the corner of cells. And there was actually no capability for displaying cell values. So I actually got in touch with them, and the USGS actually wrote a little contract with them to add that feature in, so for a few $1,000s or something. And then, that became another feature of VTK, the ability to display cell values. So we actually had a little bit of a contribution to the development of VTK.
I felt like I was in a really great position to soak up as much as I could from Arlen. I worked very closely with Dave Pollock. Arlen and I had a lot of conversations, and he, I would say, really shaped my thinking on what MODFLOW is now. It's even less of a program and more of a philosophy of something that's well documented. It's production oriented. It's robust and reliable. It's stable. All these things were directly related to conversations that I had with Arlen over the years.